Hello, everyone. Thanks for joining us again today. My name's Charles Rice. Today, we're going to be talking about torsional vibration, and your presenter today is Pete.
Thanks, Charles. It's going to talk a little bit about torsional vibration and a little bit how you measure it in Test Lab and some practical tips and tricks. So hopefully this covers a few things for people. But it's always good to know what torsional vibration is. And here I have a trace, which on the y-axis we have RPM, along the x-axis we have time. And we can see that the RPM of whatever I'm measuring here is increasing over time. So this could be a pump, a motor, whatever it happens to be. And as the question says here, Charles, and this is the interactive part, it's you and me talking, Charles.
Okay.
Anything look a bit unusual about this curve to you?
It does look a bit unusual. It's not generated by one of these AI tools, is it? No, I'm joking. I don't know. It looks like it's a little noisy or something going on, like it's going up and down a little bit, maybe.
Yeah. Instead of like a single line like this, it's kind of got some width to it, would you say? Is that what?
Definitely.
Which it might seem a little unusual. And if we zoom in on that a little bit, we can actually see that the RPM isn't just a single value. It's fluctuating up and down. And that's, I guess, what we call torsional vibration. It's the fact that a lot of times these things like electric motors and combustion engines and hydraulic pumps, whatever they happen to be, they don't run just at a single steady RPM. They have fluctuations in their speed. And as you can imagine, we're kind of concerned about that because as the RPM goes up and down, back and forth, that might cause fatigue or damage, depending how severe the RPM fluctuations are, or create unwanted vibration or noise that we hear. And so what we're really going to talk about today is how do we go about measuring and understanding that data? If you look at any kind of rotating system, like for example, we have this combustion engine here with a piston moving up and down inside a cylinder, that piston has to come down, then change directions and go back up. And when it does that, an object that's in motion one way wants to keep going in motion, so it has to overcome the inertial forces to go back up again. So the speed of that piston, if you were to measure it inside that cylinder, is not constant. It speeds up and slows down as it has to do that reversal. Does that make sense to you, Charles?
That makes sense. That makes sense.
I guess you can understand a combustion engine isn't necessarily going to run at a constant speed because of the motion of the piston. Not only that, there's a firing event. That's that little star there I'm drawing on the top. That's where the spark plug might be. Actually, it's over here.
Gap on that spark plug.
So it ignites the air fuel mixture, and when it does that, it throws that piston down violently. So that also causes it to, the combustion event itself causes it to speed up and slow down. But you might think, oh, well, hey, the future is electric. These electric motors, they run super smooth. They don't have combustion. But in fact, they do have something like windings. You see the windings over here?
Yep.
Yeah, and those, as you go by like the different poles and things, or the stator, it speeds up and slows down also. So, and in fact, they have a special word for, I guess you'd call it torsional vibration of electric motor, called cogging, because of that speeding up and slowing down due to the way it's constructed. I think maybe with both this example and the combustion engine example there, Charles, what would make it run smoother? If you had a lot of windings or just a few windings? A lot of cylinders or just a few cylinders?
I say a lot of windings would make it run smoother with the electric motor.
Yeah, because each one of these is a speed up, slow down. So you would have less time between speed ups and slow downs if you had 20 of these things versus 10 of these things. Same thing with combustion engines. That's why a V8 engine could run smoother than a 4-cylinder engine. Nowadays they got 3-cylinder engines and things like that, because the time when something else ignites or passes by, there's less time, less slowing down between events, but it's obviously more expensive to manufacture. So there's a balance there trying to make it run smooth. And then you got things like this universal joint. You can imagine it's twisting around, allowing things to run at an angle. This also will create speeding up and slowing down. Like that might be twice per rev in this case. Does that make sense to you, Charles?
Yeah.
Yeah, there's just all sorts of things that can cause the RPM of something to fluctuate. And I guess this is even potentially another cause. If you have a shaft, it's also possible the shaft has a natural frequency or resonance where it twists from one side here to the other side. There's going to be a delay in the RPM. So it's a bunch of fluctuations. And these RPM fluctuations cause all sorts of things. For things not to run smoothly, people want to lock up at lower speeds, like on a car, for example, for fuel efficiency. But at lower speeds, the torsional vibration is greater. It's going to wear things out, etc. We need to be able to measure torsional vibration and then hopefully do things to reduce or eliminate it as much as possible.
Sounds important.
Yeah. All right. How would we measure torsional vibration? So we have to measure the RPM of something. We can take an optical probe like I showed here, and this optical probe shines out a light, right? And then you have a rotating shaft, and on the shaft you might have some reflective tape like it says here, and every time the tape goes by, we had one piece of tape, we would know how long it takes for one revolution, and we could estimate the RPM. Now you can see here an example of that, but instead of one piece of tape, what have we done in this case, Charles?
Looks like we have lots of points where we're going to get reflections as it spins around. So we'll get lots of pulses back as it spins in one revolution.
Yeah, and that's very typical of torsional vibration measurements. We want to detect speed fluctuations that occur within one revolution of our rotating system. And so to do that, we need actually more than one pulse per rev. We need multiple pulses per rev. And so that's why in this case, the shaft has something called zebra tape on it, a bunch of black and white stripes that create multiple pulses per rev. Another way people might measure torsional vibration is using something called a mag pickup. And if you ever used these, Charles, they don't require any power. They have a magnet there. And this magnet, as a steel tooth goes by from a gear, it will create a pulse. And so these are kind of nice. If you're measuring torsional vibration and you have gears in your system, you can point a mag pickup at a metallic gear to pick up the multiple pulses per rev.
That's pretty handy. You don't have to put any tape on.
Yeah, no tape or anything like that. So here we got, for example, our mag pickup pointing at the gear, and you can see it's creating a pulse every time the gear tooth goes by. Here's another technique that people use to pick up torsional vibration. So maybe I don't have access along the length of the shaft, but at the end of the shaft, I have access because as you can see here, I got an exposed flywheel at the end of the shaft. And if I didn't have a gear, so maybe like this one's a good example, I could affix this zebra disc on the end and then point my laser straight at it. And then I could pick up the multiple pulses per rev as it's rotating around. And obviously, the more divisions I have, the more fluctuations I can pick up. Making sense so far?
Yeah, very similar to the zebra tape.
Yeah, similar but different, right? Zebra tape is along the length of the shaft. You wrap it. This is at the end, and you point straight at the.
Because I guess with this, you don't have to worry about, per se, the zebra butt issue.
Yeah, we'll get into all the issues in a second. I'm just trying to give you an idea of some different ways here. But maybe one issue, you notice this one says 40 divisions up here. This one says 100 divisions. Which one's better to use, Charles, you think? Is there one better? Or why would you use 40 versus 100?
I guess it depends on the order, maximum order I need, number one.
Yeah, if you think about the number of divisions there, it tells you the maximum fluctuation over the revolutions that you can measure. So if there's 40 divisions, it's kind of like DSP where you sample at twice the frequency of interest. This means I could look up to at least 20th order. Whereas here with 100 divisions, I could look up to 50th order. So it's exactly half the number of divisions is the maximum order I could analyze or see.
Yeah, I can see the advantages between the two now.
Now, let's say I got a gear it's rotating this way. See that? And like 4 or 5 teeth went by, so I see these pulses. And then my gear spins the other way, same amount. Would this signal look any different?
No, wouldn't.
No. So with all these things that I just presented, if the system was going forward or backward, you would not be able to know. The output here, the number of pulses is the same regardless of the direction. Would it be a problem if your rotating system started rotating backwards?
Yeah, I think we would want to know that.
Yeah, you probably want to know that. Some systems are not designed to rotate backwards, like a combustion engine. So if it was rotating backwards, you have a big problem. If you have something like an electric motor, those are actually designed, they can rotate equally well forward or backward. But again, you wouldn't know with an encoder like we're talking about here, whether it's going forward or backward or not. There are devices that allow you to tell the difference. So there's just another one, something called an incremental encoder. And this actually has embedded in it, it has 3 signals that come out of it. One is a 1 pulse per rev, so you know where 0 degrees is. And then it has 2 multiple pulse per rev signals with a known offset apart. And that offset is different in this direction than in this direction, right? You see there's a bigger gap here than here. Mm-hmm. And it's able to tell then, based on that pattern, whether this is attached to a rotating shaft, and it can tell if it's going forward or backward. Have you ever had to use an incremental encoder there, Charles?
A couple times.
Yeah, I think you even did a webinar on that, right? Where you used our special, we have a special card in the SCADAS front ends called the RB4 card that allows you to use these devices. Yeah, depending on this torsional vibration, how severe the fluctuations are, whether you're interested in the systems going forward or backward, you might need to use something like an incremental encoder because it can tell what direction things are rotating in. How do we analyze some of this torsional vibration? So we start out by having a bunch of pulses. We look at the time between pulses and we calculate an RPM. So we would hopefully get this somewhat funky RPM time curve that has fluctuations in it. If it looks very smooth, either you have no torsional vibration in your system or you're maybe measuring 1 pulse per rev and missing out. Then with this RPM time trace, we typically would do an FFT on it. And we would get this series of FFTs over time. And these are a bunch of spectrums where we have frequency on this axis. The overall RPM here, in this case, this RPM is going from 1,000 to 3,500. Here it would be going from 1,000 to 3,500. And then the FFT of this data, this is not vibration and acceleration or sound. This is RPM. You get RPM over here, which is the amplitude of the RPM fluctuation. Notice that this is a lot less. That's 61 RPM as opposed to this one, which is 3,500 RPM. This is how much that RPM is varying around the main RPM. If you have your RPM here at, I don't know, 1,000 or something, and then the RPM is going up and down, you know, you got your plus 60, your minus 60. That's what this number is.
Gotcha.
And we can do things like an order cut. So again, this order cut might go from 1,000 up to 3,500. And then this one, you can see this goes up. It's hard to see there, but it goes up to about 200. And this is the amplitude of the fluctuation in RPM. Charles, one thing to notice here is as we're going up in speed in this area, what's happening to our torsional vibration?
It definitely looks like it's going down as we're going up in RPM.
Yeah, it's going down. And that's because the combustion events or the windings, the time in between these things starts to decrease as you go up in speed. So it tends to run smoother. So a lot of things, like hydraulic pumps have these little veins or little compartments in them, and they cause pressure fluctuations. The higher you go in speed, the smoother it runs until something happened here. What do you think happened there?
Looks like we hit some type of resonance.
Yeah, so that picture I had earlier of that shaft that's twisting, That might be a thing where we have a rotating system has a resonance, and so instead of smaller fluctuations in RPM, we get bigger fluctuations. And so something like this, we'd have to address the resonance. Something like this, if we wanted to decrease it, it might design it with more hydraulic vane compartments or more cylinders, or try and make the speed up and slow down between events be less severe. What that FFT is doing for us is when we measure the RPM on the other page, I drew something like this where maybe at 1,000 RPM, we have these fluctuations plus or minus. When we do an FFT and we have a constant value, so constant value like this might be the 1,000 RPM, right? This overall RPM is a combination of both the fluctuating part and the overall RPM. Something that's constant in speed like this, if I did an FFT, Charles, what frequency does that have?
0 hertz.
That isn't fluctuating, so that goes right to 0 hertz. And then the fluctuating part will go to whatever frequency it's fluctuating at. So our 1,000 RPM is over here, and then our 60 RPM is over here, and that's why we can cut an order or whatever in order to tell what the fluctuation in RPM is. And we had 5 RPM plus 5 RPM fluctuation minus 5 RPM fluctuation. And we were cutting an order or whatever, trying to describe the fluctuation in RPM. One way we could do that is to say that's plus or minus 5 RPM. And a lot of times people call that plus or minus 5 RPM peak. But the total RPM excursion here is 10. So 10 RPM peak to peak. When people talk about torsional vibration, it's probably a good idea to know if they're talking about peak or peak to peak. Wouldn't you agree with that, Charles?
Oh yeah, that seems like that can make a difference on the target.
And yeah. A lot of times the convention is to talk about the peak to peak excursion. But be sure you know when people are talking about the RPM fluctuation, whether they're talking about peak or peak to peak. Here I have a shaft, the same shaft, I had 2 encoders. And one encoder had just 1 pulse per rev, another one had 120. So can you tell which one's which here?
Yeah, I think it's pretty clear.
Yeah, this green one looks a lot smoother, and then this blue one looks like it has a lot more fluctuation, because with the higher pulses per rev, I can pick up those fluctuations.
Yeah.
When you're driving around in your car, Charles, what type of encoder do they have for your engine RPM? You have like one of those fancy cars that shows the engine RPM?
I guess so. I wouldn't call it fancy. I would say 1 pulse per rev.
Yeah, they purposely don't let you know that your engine speed is varying up and down, right? People would kind of maybe freak out if they saw it jittering constantly. There can be an advantage to showing just the overall RPM and not showing those fluctuations. That's an important consideration when you're going to measure. Let me see if I got some data and stuff here that I can show. I think first of all, original data here. One of the things that we need to do is make sure that we use a high number of pulses per rev, and then we can measure those subtle fluctuations in speed. Here I have some data that I acquired. This is a torsional RPM map, if you will, Charles, and it's got frequency here, RPM here.
Yep.
That's the overall RPM. And then it has the RPM, and I guess maybe just to color it a little, we put it in dB so it was easier to see the torsional vibrations. But this is also RPM. And again, why is this one going up to 80 RPM and this one going up to 3,500?
So on the left-hand side there, of the y-axis, we have the overall RPM, and then on the right color scale, that's the fluctuation that we're seeing as it's going.
That's the fluctuation. Yeah, and I can come in here and I can say, hey, I want to see that fluctuation as a function of speed, like maybe on this particular order. So I'll pick processing, I'll drop that in. And in this case, do I have a big torsional resonance in my system?
No, you're looking pretty good. No, it's that slight bump there, but it's not too bad.
Yeah, slight bump. And again, it's higher at the lower speeds and then comes down pretty nicely as we go up in speed. So yeah, I got plus or minus 16, 17, 16 and a half RPM here, right?
Yep.
At 2000. Well, that was a trick question. What's my units over here?
Oh, RMS.
Yeah. So to know what my fluctuation is, I want to go to processing here, and I can switch to some of these other modes. So if I pick peak, now that's plus or minus 23 RPM. Does that make sense to you, Charles?
Yeah, that makes sense.
Yeah. And if I wanted to know like the total peak to peak, I would come here back to processing, pick peak to peak, and that's 46. Another kind of interesting thing that people often think about with torsional vibration is here you see it's in RPM. That's the speed of the fluctuation. But sometimes it's nice to know the absolute fluctuation instead of in revolutions per minute or per second traveled. Instead, we'd want to know maybe in absolute revolutions or in degrees, the distance traveled. That's just an integration. So if I go to processing here and I pick integrate, notice it just changed that to degrees, Charles.
Yep.
And I have done peak to peak. This is fluctuating plus or minus 0.58 degrees total, 0.58 degrees total at this RPM. These lower speeds, I'm getting up to like 3 degrees of total deflection in my shaft. That's the type of number that you might be able to use to assess the durability. Like, can my shaft withstand being twisted 3 degrees constantly? And you might even have 2 encoders and measure the difference across the shaft to see how much twist there is, right? At the beginning and at the end, in order to see what kind of deflection you have.
Makes sense. That'd be interesting.
So when you're doing this torsional vibration, again, you'll do a high number of pulses per rev. Let me just point out some more tips for when you're using the software. So I got tachometer here, and that's in RPM. And I got another tachometer here. You can see that that one's more suitable for torsional vibration.
Definitely.
Because it has fluctuations. But here's the thing too, in our software, when you go to time data processing and you're going to calculate an order, you come in here and you pick like tachometer to track on. It does not calculate orders from a tachometer channel. It only calculates it from channels that are marked vibration or acoustic, right? If I go to the FS acquisition, vibration, acoustic, or other. So sometimes, depending how you measured your data in test lab, it might be marked as a tacho, but you'll be hard pressed to actually do a torsional analysis, extract an order from it because it says tacho. The trick is to say, okay, if I wanted to use this tachometer, maybe I set it up with a high pulses per rev, is to say I want to take that data, like that channel 1 here, for example, and I want to do torsion on this, whatever the engine speed or whatever, but set this channel group then to something other than tacho, vibration or other or whatever. And when you do that, this is just the same data. In this case, it's very smooth, so you wouldn't really use it. But I just wanted to illustrate the principle. Yep. If it's in the vibration group, then you can calculate orders from it. Does that make sense to you, Charles?
That's a good tip.
See if I can go one step further with that tip. But yeah, let me go into test lab signature here. So I think this is something that maybe a lot of people may or may not know about. And that's when that you're setting up a tachometer, you might be like, well, how am I going to get the tachometer to be both a vibration channel and a tachometer? It seems like it has to serve 2 purposes, right?
Yeah, would they try to tee it, a lot of people?
Some people might tee it, physically tee it. But it's also possible if you have a tachometer like this, you can go in here, and if you pick vibration, this is maybe an unknown trick, then you can use it as both a tachometer and a vibration channel without teeing it. That's your, I guess, virtual tee, if you will. Were you aware of that one? Yeah.
I was aware of that one. That's pretty cool. And so I will actually still get a tacho channel that will say tacho, and then I'll also get another dynamic channel for this tacho one. Is that right? And the vibration.
Yeah. So it's not a mistake that we allow the tachometer channel. By default, it's set to tacho group, but we also let you put it in the vibration or the other group so that you can do things like this torsional analysis and still use it as a tacho. And you don't even have to do any teeing physically.
Nice.
Hopefully that was a good tip.
That's a good tip. We're going to save a lot of money in tees now, BNC tees.
Yeah, thousands are just saved by that tip. Let's look at some other data here. All right, so I got a signal here. This is from a mag pickup. And you can see that we got a bunch of pulses. There's 36 pulses, or at least there should be, but this particular gear that I'm pointing my mag pickup at, Charles,
yep,
it's missing a tooth. Can you see where it's kind of missing there?
Oh yeah, that larger gap there.
Yeah, there's a larger gap in time. And it's not uncommon that a gear might have one missing tooth for indexing purposes. And so if I was to use a formula like tacho pulse to RPM, there's all sorts of formulas here to calculate RPMs. I'm using tacho pulse to RPM. I could say, okay, well, there's 36 teeth, at least there should be, and it's crossing 0 volts. So I'll say 0 here. And then I do my calculation, put in the numbers, calculated the RPM, and should I be concerned about my RPM calculation here?
Yeah, I would be concerned. I would be concerned.
So it's dipping down right where that missing tooth is, because it looks like it's momentarily slowing down, right?
Yeah.
Because of that large gap. So that's something that we don't want. Now, in the tacho pulse to RPM command, and you have this both online and offline, there is a thing for if you're missing a pulse called a missing pulse correction. And you can see that's set to 1 here. This will try and fill in and compensate for the fact that there is 1 missing pulse per revolution. Okay, shall I calculate that and see what it looks like?
Yeah, let's try to make this a little bit better.
And I can actually set this to overlay. What do you think, Charles?
Wow, nice.
It's quite a bit better.
The way you fixed that missing tooth, you could be a dentist, Pete.
I didn't even know I had it in me. Yeah, so it's got some good corrections. Now, one thing that's interesting about this is you see there's some different options here. It also can recalculate the pulse before or after the missing tooth. And why do you think we have that option in there? What do you think?
Looks like that gap is affecting the pulse after for sure, it looks like.
Yeah. So what happens is with these magnetic pickups, the ones that I was showing earlier, you can see that this one is a lot different in amplitude, and that actually distorts where the crossing is of this one. Even this one is not correct. We're missing one, and then because of this distorted amplitude, the timing isn't quite right here. We typically would do something a little more sophisticated with our missing pulse correction, where we recalculate the before and after. And that would look something more like this. It can fill it in a little bit better. So a lot of times you have to fool around with different schemes depending on whether if you have distortion here due to mag pickup. So we have corrections in the software. That's what all these different correction schemes are. They will even look at the pulses before and after in case they've been affected by the missing tooth. Part makes sense so far, Charles?
Yeah, no. Very cool tool.
Here's another thing that can happen. So we were talking about this tape, and we put it around this shaft. right? And then go and do some measurements. But I think you alluded to this. You said there could be a joint where, you know, the piece of tape overlaps with where you laid down the tape originally, and then you get something like two pulses that are really close together or farther apart. Again, if I go back maybe to that original slide here, we have this right here that's extra thick. So it's hard to make the stripes to print out something that is exactly the right diameter of the shaft.
Indeed.
That will cause an anomaly in our RPM, right?
Yep.
So let's look at that. Go in here, and I'll just grab that data. Okay. So we got this. The same thing happens, and in this case, we have a dip in RPM every other revolution, and that dip is caused by a gap in that tape. And then we have a different correction. In the case of the zebra moments, this is actually not evenly distributed around the shaft,
right?
Because it didn't overlap perfectly. So the missing pulse correction wouldn't work because it's not just a missing pulse. We actually have to change every single pulse to get it back so that it's evenly distributed around the shaft. And that's what this zebra moment correction does. And if I do that and I overlay that, we can correct for that as well. So that's not uncommon with something like zebra tape. Did that make sense to you, Charles?
Yeah, no, that makes sense.
Yeah. All right. Another nice thing is in our software, you could have several encoders on different systems, and it's possible to visualize the torsional vibration of each one of these encoder locations. See how there's like a little piece of pie in that circle, Charles?
Yeah, I see the pie moving there.
Yeah, and in the pie, you see like a line going back and forth. That shows the maximum excursion. So we know that this one's twisting more than this one, for example. And we can also see the phasing, like if something's twisting in or out of phase with something else. These are called torsional nodes. And you can basically create an animation of the torsional vibration in your system. That makes sense?
That's pretty cool. You can see the phasing with that one that's moving inside the pie slice. That's very cool, actually.
And that's a standard feature in the test lab geometry. And by the way, you can also use translational vibration. So you can have a combination torsion and all the translational vibrations of your system. To create one of those pie-shaped wedges, it's with this torsional node. You just add a disc on a point here, and then it'll create that torsional node for you. So that's another option for things that you can build up and put in the geometry. All right. I think that was everything I kind of wanted to cover today, Charles.
Thanks, Pete. Excellent. Thought you gave us some great tips as well as great background information. And I definitely like the geometry there with the torsional nodes, phase tracking. That's pretty cool.
Thanks, Charles.
Thanks, Pete.